Okay, so welcome to the last morning of the school. We have a exciting, short but exciting program for you. My name is Gabor Csanyi, and two talks in the morning, and then a practical session with a couple of tutorials which you can click through and also do your own calculations. So the keynote talk will be given by Anatol, and it's on machine learning and molecule in chemical space, molecular space. And then there's a shorter talk afterwards given by James Kermode on the materials side of things. It's about learning potentials from forces. The tutorials have been created and organized by Adam and Martina. I thought I'd like to start with just a very brief introduction, my own, again, very brief take on where this field is at the moment, without taking any of the thunder away from Anatol and James. So you have had a little bit of machine learning earlier in the week, and really this is just a way to introduce the topic. Machine learning is about function fitting or compression. Really just two different tasks that we need to do. And both of them are to do with very complicated functions. So when you're doing compression, you're given in some very high dimensional space examples of where that function is interesting, but you don't get to see what the function is. So, and that's usually called probability density estimation, or other names of it are like unsupervised learning. So if I imagine that you're a child going out into the world and you see images through your retina, no one tells you what they are, at least even if they do, you don't understand that. So what you're getting of the input you're getting of the world are images that are likely to be encountered, as opposed to other retinal input that isn't encountered. And that's it. That's the input. And what you're learning, or what the machines are learning when we try to train them, is to be able to summarize in the machine itself what are the likely things that are likely to be encountered. How do we express them compactly? And that's why I'm calling it compression. Function fitting is when you get input data, where the input data are pairs of inputs and targets. So when it's called supervised learning, when you're told that this function has this input and this is an example output, you get given many of those, and then your task is to develop a model for that function. So the functions that we're talking about, both for supervised and unsupervised learning, can really be unknown in the sense that there may not be a closed form procedure to compute that function, and that's the case for finding images in faces in images. There isn't a way to compute deterministic. There isn't an algorithm which tells you whether there's a face in an image and whose face is it. You get to build that approximate function just by looking at the examples. More closer to the materials field, if I want to predict the performance of a material based on its composition, based on maybe experimental data, based on the history of metallurgy, then there is no deterministic function that tells me the answer, but just by the examples, we're supposed to build up a model that approximates that. Alternatively, maybe there is a function that tells us the answer, but it's just very expensive. So in the context of chemistry and materials modeling, there is quantum mechanics, and we can actually compute the properties of materials from first principles, but it's so very, very expensive that you want to use machine learning to speed that up. And speeding up, I don't mean like you optimize your code and it's 2 times faster. I mean, speed it up so that it's 10 to the 12 times faster, maybe. Instead of solving the full many-body Schrödinger equation, if I'm able to predict the energy of a molecule, having done a bit of machine learning and fitting the function of the energies of molecules based on their structure, I may achieve enormous gains in speed. And that's what, in fact, our speakers are going to be engaged in doing. So going from atomic coordinates to the quantum mechanical total energy is a task in which we're looking for enormous speed-ups. And it looks like, it's the one function we're trying to fit. A lot of us are engaged in trying to learn just this one function. And we've been doing it for a number of years, and I'm sure we will do it for considerably many more. It is a very complicated function, but the payoff is very large. So I want to give you my one-slide summary of Gaussian process regression, which is a particular machine learning algorithm that today's speakers have used a lot in their research. And in fact, many of the tutorials this afternoon are also based on this. So it's a little bit of formalizing of the second way of doing the function fitting type of machine learning that I just mentioned. So suppose you have pairs of examples, x and y. X is the input space, could be high dimensional. And that ansatz up there on the left is in fact the function that we're going to fit with some unknown parameters alpha. So fx is a sum over basis functions. Basis functions in this approach are called a kernel, and that is because they're typically symmetric, and typically they have an interpretation which is the similarity or dissimilarity of the function at two different locations. So if I have on the right-hand side, there's an example of a Gaussian kernel. If I have locations x and x prime, how much do I expect the function that I'm trying to learn to be similar at those two locations? And if the two locations are the same, that Gaussian has a value of 1, and that corresponds to the function values being the same. If they're very far apart, the Gaussian decreases. So it's very easy to determine the unknown coefficients alpha. You substitute in your data, x and y, and you get a system of linear equations. So linear equations are typically, that system is typically very badly conditioned. It could be underdetermined, could be overdetermined. So it's quite typical to regularize it, to add a diagonal component, which I indicate here by that sigma nu. And once you add that diagonal, it's easy to invert that function, invert that matrix, and get the coefficients. Right? So the K matrix is just the basis functions evaluated at the pairwise locations of the input data. You add the sigma nu to it, so you get a regularized covariance matrix, and you invert that, and that gives you the answer. And it's unique given the data and given the parameters of the kernel function and the regularization. And using those alpha coefficients, having solved the linear problem, I can write the machine learning answer in a compact closed form. So f of x is just kt transpose c inverse y. Now, that's the most simplified version. Of course, when you do it in practice, you may have, that matrix may be very big. So you may have to do some tricks to invert that in reasonable time. You may have data points that are not the function values, but derivatives. One of the talks is about that. Or the function you may be getting data on the sums of the function values rather than the function values themselves. So of course there is a practice to it, but this is essentially the bottom line. So why is this hard to do? Imagine that we're trying to evaluate a function at that red location. I have database points at those blue locations with some basis function, which I drew up there. Why is this so hard? Well, there are a whole bunch of parameters or choices to be made. So which kernel is best? Do I want to always think about which kernel is best? Are there kernels that always work so that I don't have to think about them? Are there kernels which have parameters that are easier to optimize than others? How do we incorporate quantum mechanical data in the most efficient way? Again, there are lots of choices in what we compute quantum mechanically. What is a good protocol for setting parameters? We think about machine learning because we want much, much faster quantum models, and that's because we want to evaluate these functions many, many times because we're doing high throughput screening or we're doing other kinds of materials discovery. So the balance between human effort in and machine effort has to be considered. So I may prefer a protocol that leads to a function that is slower or somehow suboptimal if I don't have to optimize its parameters, if I don't have to, if I can reduce the human time which is needed to specialize the method to my current problem. And I think a lot of these problems people have thought about, and we do have some answers, but how to build a suitable database, I think, is one of the questions that is going to loom very large in the coming years. So given that we understand our kernels, our basis functions, our parameters, now we need to get data, and how do we get that data? What protocols we use to generate the data so that we get a machine learning ansatz that is suitable for doing science? That's, I think, is the big question. And it's somewhat reflected in what happened in my own group. So this is a somewhat tongue-in-cheek history of what I've been doing. From 2004 and 2010, I've been learning the basics, just like some of you have been recently, just mucking around, basically trying to read papers in machine learning, playing things with very small examples. And then between 2010 and 2013, I felt that we actually got some in-depth understanding of what kernels mean and why one kernel is good and the other isn't, and how to incorporate symmetries properly, and whether we want to incorporate symmetries and how important that is. And I feel that we gained some understanding. And now, in the last couple of years, we've been learning to build databases by hand, very laboriously, one student per material, one student per scientific question. And really, that's the stage where we're at. I don't think those things are really not automated yet. The system that I use, that we introduced, is called the Gaussian approximation potential. The Gaussian here refers to the probabilistic interpretation of Gaussian process regression, of the methodology, of the approach that I had on the previous slide, and that's what we use to build materials models. So let me show you. Anatol is going to talk a lot about molecules, so I just want to show you a couple of brief examples of how well we can learn quantum mechanics. So we have these hand-designed databases. So on the left-hand side, I list very small unit cell configurations which we do quantum mechanical computations on and chuck them in the database, energies, forces, virials, or stresses, all sampled with MD and MC. And when we do that to tungsten, which is sort of the first work where we did this in anger on a large scale, the results are shown on the top right. The bluish colors are all existing interatomic potentials. And I'm showing you the relative error with respect to DFT. The entire database is trained with density functional theory. And you can see that they're all over the place. Errors are up to 50%. And really, doing more science doesn't help. So the three different models, BOP, MEME, and FS, span 30 years of materials modeling. So FS, Finis-Sinclair model, is from the 1980s. Then MEME is from the 90s, and BOP is from the noughties. And really, they all have different strengths and weaknesses, but really, they're not very accurate. And the moment you turn on the machine learning, and you actually need a lot less knowledge of metallurgy than all those other people have who developed those other models, you get a force field that really performs extremely well for what it's trained. So for these simple defects. We can repeat the exercise for iron, which we've done recently with Nicola Marzari's group, and on a very similar database, you get excellent accuracies, even for properties that aren't directly trained for, but of course the atomic configurations that a dislocation experiences, for which the Piles barrier is shown on the right, is represented by the database that's listed on the left. So you can see the Piles barrier, the little curve on the bottom, the green curve is the answer of the let me see this one. So this green curve is the interatomic potential that's state of the art. That's the best you can do. These little points are test points with DFT, and this is our machine learning model, and in a small unit cell, it's not symmetric, but once you make the unit cell very big, which you can do because the model is very fast, then you get a nice symmetric Piles barrier for the glide over dislocation. Here are a bunch of interstitials. This was trained from MD, on high temperature MD of interstitials are in the database, but these are relaxed configurations. And we track the DFT answer, which are these orange points. These other points are other DFT results from the literature. So highlighting the fact that even with what kind of quantum mechanics you put in is important. And the last example I want to show you is on silicon, where we're trying to take this to the limit, and the question is, can we actually put in everything? And here's a summary slide of a forthcoming paper where we really took all kinds of silicon structures, everything that we could think of by hand, having the experience, and here are a representative results. These are fractional errors, again, with respect to DFT of elastic properties, point defects, and some planar defects. And here are all the different models that are available in the literature. Here's the quantum mechanical model. And you can see that more or less across the board, the model is very, very accurate. There are a couple of places where it isn't. And in fact, those configurations, so stacking faults and grain boundaries, were not in the database. They are very far. They involve atomic environments that are very far from those in the database. And then the machine learning model doesn't perform so well. It's typically no worse than other models. And if you look at those configurations, here's one for a stacking fault. I color the atoms by the predicted error. So one additional insight that machine learning models gives you is that it knows about its own error due to its probabilistic interpretation. So these atoms show a high predicted error, and indeed that is where the stacking fault is. Those are where the new environment is. And one should go back in and add those small unit cell configurations to the database. That goes into, that starts to get into the direction of automation of database building, and that's what we are doing now. So just to finish off, before I yield the floor to Anatol, is a couple of points on future perspective. So I think we are ready for some serious science applications in some limited domains. So screening of molecules for ligand binding and organic crystals. I think we're no longer just, we've been publishing, us and other people have been publishing little demos to show that the method works, and it works very well. And I think in the coming years you will see proper science applications. In the field of materials, I think we can do structure search. We can start to compute phase diagrams, and we can look at structures of amorphous materials. These are all cases where DFT is accurate enough, but too slow. And there is some science to be done here with much faster models. In the development of force fields, I think we will still need to widen the areas of applicability. Alloys, interstitials, dopants, lots of different atoms. People haven't published a lot on that. Metal oxides are notably absent, and that's where, of course, traditional force fields just have not existed because they're so difficult to do, and machine learning is hopefully the silver bullet, but we need to work out how to deal with long-range interactions. And then in generally making biomolecular force fields or force fields for hydrocarbons is something that the next step for these machine learning models. I think there is some work to be done on the methodology, and that's, as I've been emphasizing, is mostly around database building. So how do we formalize the building of a database? How do we give guarantees of what the databases can do? I'm also personally very interested in exploring the trade-offs. So the models that I've been illustrating here, so the silicon, the tungsten, the iron, are quite slow in the context of force fields. So typically 1/10 of a second per atom, per CPU core. 1,000 times slower than a pair potential. Many times faster than DFT, but somewhere in the middle. So can we trade off accuracy and computational cost? So far, we've been concentrating on accuracy, and so have other people. And we say, okay, the computational cost will be improved later. But I think we've achieved the accuracy now, so now it's time to think about that trade-off more explicitly. So that's by way of introduction. And I'd like to ask Anatol to come and give his keynote presentation.
Okay, so I think we've been keeping you a good schedule. I'd just like to show you in like 1 minute what the tutorials look like to whet your appetite, and then we should have a half-an-hour coffee break and meet up in the computer room at around 11:30, and that gives you an hour and a half before the lunch break. So we have 3 tutorials for you, and 2 of them you can reach from, let's see, what's the best place? Here's the URL. We'll write this up in the up on the board in the computer room, and they come as Jupyter notebooks. So one of them is on iron grain boundaries, and the other one is learning of atomic charges. I'll start with the second one because it's shorter. So once you fire up the notebook, you'll see something like this with a little explanation, just rehashing the Gaussian process formula, which you will see programmed in. We have a database. Let me just try to run these things here. And you load up a database of molecules. Actually, it's the same database that Anatol has used, 134,000 or small organic systems, but this is only a subset of them, 1,000 molecules, and they sort of look like that. You can view any one of them. Here's another one. Okay, so these are the molecules in the database that we load up, and we're going to learn their charges. So here's a bit of introduction on how we do that, what the kernel is, and then once you click that through, you will find that with the default parameters, the learning is very fast on the charges, but it's not very accurate. And then inspect the code. It's very short, but at the end, there are a bunch of interesting tasks that you could carry out. Making the fit a bit more accurate, extending the cutoff, making the descriptor closer to being unique, and they will all help to make the learning better. And then there are further more wide-ranging tasks below. And then in the second tutorial, which is on grain boundaries, again, it comes as a notebook, and it's with a little introduction, and to just tell you what grain boundaries are, and again, loading up a database, and you start visualizing the atoms near a grain boundary and classifying them according to their local environment. Let me see if there's a view here. Yeah, I don't know where the views come in this one, here. So here you see a grain boundary, and you can zoom it around and inspect the atoms. And then further on, the tutorial shows you how to compute simple descriptors, which allow you to classify these atoms. And then the third tutorial is on the force-based learning that James just talked about. And this doesn't come as a Jupyter notebook. It's reachable directly from the Nomad Analytics Toolkit. And there are 2 ways of reaching it. One of them is through the official tutorial page, and this is where I'm told that all the graphics is guaranteed to work right out of the box. There is a more complete version of this tutorial with longer introductions, which you can reach from the dashboard when you log in to the Nomad system, and that has, again, extra formulas that are directly relevant to this, but otherwise it's the same content. Some of the calculations are a bit more touching in this container. So I think this is it for the tutorial. Thanks very much for listening to all of us this morning. Have a good coffee break, and I'll see you upstairs in the computer room in about half an hour.